Hello and welcome to Gate to Aerospace Lab. In this video, I will be solving the propulsion question from 2007 question paper. The first question is, which one of the following engine should be used by a subsonic passenger transport airplane for minimum specific fuel consumption? See, if you see the options, then this turbo ramjet engine is a supersonic engine. Then this scramjet is hypersonic. Okay, and this turbojet engine with afterburner, we are using afterburner for the fighter aircraft. Okay, this afterburner we are using to increase the thrust with the expense of fuel. So the only option left is B. So B is the correct answer. On which of the following thermodynamic cycle does the ideal ramjet operate? You see, this Rankine cycle is for the steam power plant. The steam power plant operates on the Rankine cycle, and Carnot cycle is an ideal cycle. Okay, ideal cycle for any engine. This Otto cycle is basically the petrol engine. Petrol engine works on this Otto cycle principle, where the heat addition takes place at the constant volume, right? Our ramjet engine operates on the Brayton cycle, and all the gas turbine cycle works on the Brayton cycle. See, in this, air enters through the eye of centrifugal compressor with a stagnation temperature of 300 Kelvin, and this problem, the entrance stagnation temperature is given, and exit the compressor with a stagnation temperature of, so you are having T01, that is the entry stagnation temperature, as 300 Kelvin, and at the exit it is 424 Kelvin. If the isentropic efficiency is given, and it is as 0.81, and the specific heat of the following gas, the value of gamma is given, that is 1.4. Then we have to find out the pressure ratio across the compressor. See, for a compressor, if you draw the TS diagram, okay, it will look like something like this. Okay, this is P2 delivery pressure, this is the entry pressure. This represents the ideal isentropic process. This represents the actual process. Okay, this state is 1, this state is 2, and this state is 2 dash. Okay, now the efficiency, isentropic efficiency, is defined as T2 dash minus T1 divided by T2 minus T1. Okay, so if you will take T1 common from this, this will become T2 dash divided by T1 minus 1 divided by T2 minus, we will write this in the form of stagnation temperatures. Okay, so I will add 0 here. So this is T01, this is T02, T01. Now this will be equals to T02 minus T01, which will be equals to 124 Kelvin. Right, from this data you can find out this 124 Kelvin, and T01 is 300 Kelvin. In the next step we will substitute that value also. This is 300 divided by 124, and we know that T02 dash by T01 will be equals to P02 dash by P01 divided by gamma minus 1 by gamma. Okay, so this will be equals to, and this is given to us, the value of value of gamma is given to us. Yes, right. Okay, this we have to find out. Gamma we have to, this one we have to find out. The pressure ratio we have to find out. So this will be equals to pressure ratio to the power gamma minus 1 by gamma minus 1. Okay, so neta I is given as 0.81 into 124 divided by 300 plus 1 Rp to the power 0.4 divided by 1.4. So if you solve this, you will get the value of Rp, which is equals to 2.75. Okay, so this is our answer. Option A is the correct answer. Right? Next question. For a impulse turbine, okay, this is very important. The impulse turbine with identical stages, the hot gas exit from the stator blade at the mean blade height with an angle of 70 degree. Okay, that means what? You are having alpha 2 as 70 degree with an axis of the turbine. If the absolute inlet blade angle with the axis of the turbine at the mean blade height for the rotor blade is 37 degree. Okay, now if you see beta 2 is also given, that is 37 degree. Then the absolute exit blade angle we have to find out, that is they are asking us beta 3. Okay, with the axis of the turbine. Okay, now we will draw the velocity diagram for the similarly. Okay, this is the diagram. This angle is alpha 2. This angle is our alpha 2. This angle is our beta 2, and this angle is our beta 3. Now we know for a compressor, the degree of reaction is given as Ca by 2U tan of 3 minus beta 2. Now this we know that for impulse turbine, we are having the value of R as 0. Okay, well, if this value has to become 0, then these two values should be equal. This implies 10 beta 2 should be equals to 10 beta 3, or you can say beta 2 is equals to beta 3. Beta 2 is known to us, that means beta 3 will be 37 degree. Okay, so B is our answer. And the next question, they're asking in which one of the following materials should be selected to design an axial flow turbine at the high turbine blade at the high temperature. See, this is a memory based question. Actually, nickel is used for in all components working at the high temperature. Okay. The next is, which one of the following statement is true? See, the isentropic efficiency of the compressor is constant throughout the compressor. Yeah, this is correct, because earlier we have seen that the isentropic efficiency is the function of inlet and exit temperature only. Okay, so this is correct, but anyway we will check all the statements. The flow separation is critical in axial flow compressor, and we know the pressure ratio of a centrifugal compressor approaches to 0. No, this is also wrong. Then centrifugal compressor are always designed for multiple stages. No, it will be very complicated if you design the centrifugal compressor for the multiple stages. Next, this question: onboard rocket motor of a satellite has an initial mass of 2000 kg. So we know what is the initial mass. Okay, this is 2000 kg. Provides a specific impulse. The specific impulse is given as 280 seconds. Okay, if the motor is fired to give a speed increment of, that means delta V is 500 meter per second along the direction of motion. Okay, the mass of the propellant consumed. So we have to determine the mass of the propellant. You see, we know that when a rocket fires, okay, when a rocket fires, we know the velocity increment, that is given as g naught by ISP ln initial stage. Then what is M1? M1 is the mass of the stage, mass of stage at T equals to 0, that means before start of burning. And at what is M2? M2 is the final mass. Final mass means what? When you burn all the propellant, then what is the mass left out? That is the stage mass. Okay, so what is how we can determine the propellant mass? The propellant mass will be equals to final mass minus final mass minus initial mass. No, this will be equals to initial mass minus final mass, M1 minus M2. Okay, now in this question everything is given to us. Velocity is 250, this will be 9.81, ISP is 280 ln M1 by M2. Okay, so here if you will plug in the value of M1, which is given as 2000 kg, this will be equals to 2000 kg. Then you will get the value of M2. The value of M2 you will get as 1667.5 kg. Okay, so mass of propellant, from this equation we can determine this will be equals to 2000 minus 1667.5 kg. This will be nearly equals to the 332.85 kg. So our answer will be B. Okay, now in this problem the combustion equation is given to us. Okay, this equation is the combustion equation. In this C8H18 is our fuel. Okay, this is our oxidizer. Now, and this is our product of combustion. The mass of the each elements is given to us. Then what they are asking to us is that it is told in this question that we are using an air to fuel ratio, fuel to air ratio as 0.028. Okay, then they are asking us to find out the equivalence ratio. What is equivalence ratio? Equivalence ratio is defined as what is the fuel air ratio on which your engine is operating to the fuel air ratio required for stoichiometric reaction. What is a stoichiometric reaction? It means that you are providing oxidizer in the proper amount. The amount of oxidizer is not less, not more. Whatever required, exactly that much only you are giving for the combustion. Fine. In this, if you see, we know this fuel to air ratio what we are using. Okay, now we have to determine the fuel to air ratio for a stoichiometric reaction. How to determine that? You see, what is the fuel mass of fuel to the mass of air? This we will find out. What is mass of fuel? How can we determine? This will be 2 into 8 molecule of carbon. Okay, 1 molecule of carbon has a weight of 12, so 12 into 8 plus 1 into 18. Hydrogen has a molecular mass of 1 divided by this is 25 molecules of oxygen. That means 25 into this is 16 into 2 will be 32 plus this will be 94 into 2 molecules of nitrogen, that means 28. So if you will compute this, it will comes around 0.0664. Now you know this value also. Now you just plug in here, so you will get the equivalence ratio as 0.028 divided by 0.0664. So this will be equals to 0.422. So your answer is B. Fine. Next, in a rocket engine, the hot gas generated in the combustion chamber exits the nozzle with the mass flow rate. The exit flow rate of the mass is given, that is 719 kg per second, and the velocity with which it is existing is 1794 meter per second. Okay, we know the velocity of exit. Then mass at the exit, mass rate flow at the exit. Then area at the exit is also given, that is 0.635 meter square. Okay, the nozzle expansion is optimum. Okay, what is optimum expansion? That you are expanding to the atmospheric pressure. Okay, then the thrust produced. You see, the thrust equation for a rocket engine is given as mass at exit, then velocity of exit to the nozzle plus PE minus PA into this is the pressure thrust, this is the momentum thrust. Okay, the thrust will be equals to 719 into 1794 plus this will become equals to 0 as PE equals to PA. So the thrust will come out 1289.88, which is, you can tell it's 1290 kg. So B is our answer. Next, a gas turbine operates with a constant area duct combustion chamber with the inlet and outlet stagnation temperature. Inlet stagnation temperature is 540 Kelvin and outlet it is 1104 Kelvin is given. Okay, so assume that the flow is one dimensional. Okay, incompressible and frictionless. Okay, that there is no irreversibility in the system. That is the heat addition. The heat addition is driving the flow inside the combustor. Okay, the pressure loss factor, which is defined as stagnation pressure loss. Okay, which is non-dimensionalized by the inlet dynamic pressure. If you see, it is telling pressure loss factor is given as change in stagnation pressure to the dynamic inlet dynamic pressure at inlet. Okay, you see here it is given in the question that our flow is frictionless, so there is no irreversibility in the system. So the change in stagnation pressure will be equals to 0. So if this is 0, this pressure loss factor will become equals to 0. So A is the answer for this. Okay, problem number 11. A diffuser of an airplane engine decelerates the airflow from flight Mach number. Flight Mach number is given. This is equals to 0.85 to a compressor inlet Mach number, which is equals to 0.38. Assume that the ratio of the specific heats is constant, that is equals to 1.4. The diffuser pressure recovery ratio, which is given as 0.92. Okay, this is basically the pressure ratio only. This is 0.92. We have determined the isentropic efficiency of the diffuser. Okay, first of all we will see the cycle. If you see the cycle, this is the atmospheric pressure. Okay, this is TS diagram, and the temperature, the static temperature is this one, TA, and the flow through the diffuser is basically a adiabatic process. Why adiabatic? Why not isentropic? Because there is a friction involved while entry to the diffuser. So there is irreversibility in the system. So it is, and there is no heat addition to the system. Okay, externally we are not adding any heat to the air. So this is an adiabatic process. Okay. Now, so this we can take it as the total temperature at A. Now, see the system. This will be something like this. This is the final state, the entry to the compression. Now, the efficiency you can write at this efficiency will be equals to T02 dash minus TA divided by T0A minus TA. Okay. Now this TA we can take common, and this will be equals to this. You can write this term as T0A by A minus 1. Okay, this we can write in term of Mach number. So the efficiency will be equals to the top term, we can write it as this T0A into T0A divided by TA. Okay, then this will be equals to 1 plus gamma minus 1 by 2 into MA square minus 1. So if you rewrite this, we can rewrite as pressure to the power gamma minus 1 by gamma into this will be equals to this into 1 plus gamma minus 1 by 2 into MA square minus 1 divided by gamma minus 1 by 2 will be equals to 0.2 into 0.85 square. Okay, if you will put all these values, the RP value we know 0.92, gamma value you know, then MA value also we know 0.85, then you get the value of efficiency as 0.8135, which is similar to our 0.814. So B will be my solution. Next question, the purpose of fuel injection system in the combustor. Okay, the purpose of this injection system is to convert the fuel in the droplets. Okay, and spray it inside the combustor chamber with a very high pressure, so that the fluid will become the droplets. Okay, so D is our answer. This is a memory based question. Next, you see this question, it is telling that we had a rocket engine with the fuel liquid hydrogen and oxygen as a liquid oxidizer. This is basically a cryo engine. Okay, this cryo engine has a specific impulse of near to around 450. Okay, so this B is our answer. This is also a memory based question only, but you should know that liquid hydrogen and liquid oxygen means you are talking about the cryo engine. This question, see, air enters the compressor. At the entry of the compressor, the velocity, the density and the stagnation pressure is given to us. That means P01 is 0.9 megapascal and the exit velocity is 139. Stagnation pressure is, okay, at the exit stagnation pressure is given as 3.15 megapascal. This also is in MPa. Okay, and value of specific heat constant is given as 1.4. Okay, the compressor pressure ratio, it's simple only. We know that pressure ratio, if you want to determine P02 by P01, this will be equals to 3.15 divided by 0.9. If you will find out this ratio, this will be equals to 3.5. Okay, now the next problem, see, and this we have already solved this problem. The next problem, see, we have to determine the isentropic efficiency when polytropic efficiency of the compressor is given. Okay, polytropic efficiency of the compressor is given as 0.89. First of all, we will see the cycle. This is TS diagram. This is the delivery pressure. This is the entry pressure. This process is isentropic, the 1, and this is state is 2 dash, and this is the actual process. This is 2. Now the isentropic efficiency we know is given as T2 dash minus T1 divided by T2 minus T1. Okay, if you will take T1 common, then this will be equals to T2 dash divided by T1 minus 1. Okay, this T1 will get cancelled. This T2 by T1 minus 1. Okay, now in the next page we'll see, we have seen that efficiency will given as T2 dash divided by T1 minus 1 divided by T2 by T1 minus 1. Okay, now we know from our basic concept that T2 by T1 is given as P2 by P1 to the power gamma minus 1 by gamma into the polytropic efficiency. Okay, and this will be, we can write it as Rp to the power gamma minus 1 by gamma. This is the isentropic temperature ratio minus 1 divided by this value will be, this is basically Rp pressure ratio. This will be equals to gamma minus 1 by gamma into P minus 1. So the value will be 3.5 to the power 0.4, 1.4 minus 1 divided by 3.5 to the power 0.4 by 1.4 into value of polytropic efficiency is 0.89 minus 1. So if you solve it, you will get the value of neta isentropic, which is equals to 0.869. So B is the correct answer. Fine. So this much question was asked in 2007 from the propulsion paper. Okay, thank you. You can subscribe this channel for the regular update, and if you want the guidance for the GATE examination for 2021 or 2022, you can call on this number or you can WhatsApp me on this number. If you want a specific topic to be discussed on this channel, you can comment in the comment box. Thank you.